Real exam questions. This is question 50 about beam design. In an office building, a concrete beam has the following characteristics. This beam has a depth of 600 millimeters and a width of 1000 millimeters. It's reinforced with stirrups, 4 legs, diameter 12, center to center 300 millimeters. Top reinforcement is 5 rebars, diameter 16. Bottom reinforcement is 12, diameters 25. Concrete cover is 40 millimeter. Creep coefficient is 2. And the concrete quality is C3037 and the steel quality is B500. So this beam in an office is subject to simple bending, and the characteristic load under the permanent loads is equal to the characteristic load under the mobile loads. Determine the moment capacity of this section in ULS persistence. Determine the moment capacity in serviceability limit state characteristic and quasi-permanent, and calculate the shear force capacity without taking account or without verifying VRDC or VRD max. The moment capacity in ultimate limit state persistence. This is the cross section before loading. That's the bending moment on it. Creates tension in the reinforcement, in the tension reinforcement, and compression in the concrete at a distance delta Gx from the most compressed fiber of the concrete. Lever arm Z is the difference, this distance between the two, and the effective depth is D. The compression reinforcement has a position at D2, and the total force in the compression reinforcement is Fs2. Now we are in domain 2A, or we will gamble, in fact, that this is domain 2A, but we will have always to check afterwards if this is correct. And in domain 2A, sigma S1, which is the stress in the tension reinforcement, so the tension reinforcement is yielding, so sigma S1 is 435 megapascal, which is 500 divided by 1.15. The filling coefficient in domain 2A is a constant and it's 0.81. The maximum or the design value of the concrete compressive strength is alpha cc times FCK divided by the material factor and gives us 70 megapascal. The width was 1 meter. D2, the position of the compressive reinforcement, is of course concrete cover plus the stirrup diameter and plus the point of gravity of the reinforcement, and gives you 60 millimeters. D1, the position of the tensile reinforcement, is of course equal to concrete cover, the stirrup size, and then the point of gravity of the tension reinforcement. And D1 is then 64.5 millimeters. The effective depth is 600 times D1, gives you 535.5 millimeter. And the tension reinforcement, it's 12 diameters 25, so it's 5,890 square millimeters. The compression reinforcement is 5 diameters 16, so which is 1,005 square millimeters. The tension or the compression in the compression force, the sigma S2, is equal to the modulus of elasticity times epsilon S2. And epsilon S2 we find from equivalent triangles in the strain diagram. We see that then the tension or the stress in the compression reinforcement could be smaller than 435 megapascal. Translation equilibrium of the section. It means that the compressive force in the concrete must be in equilibrium with the tensile stress in the reinforcement and the compressive stress in the reinforcement. So we got this equation. Of course, the force is equal to the cross section times the stress. And the force in the concrete, the compressive force in the concrete is filling filling coefficient times depth of neutral axis times the width of the sections and the maximum or the design value of the concrete compressive strength. We can now fill in the different variables that we have, but we still do not know what x is. So we fill this in what we've got in this equation in the translation equilibrium, and we can calculate x from this equation. So x is 155 millimeters. Then we go to the rotation equilibrium. The rotation equilibrium around the tensile reinforcement is of course equals to d times delta g x, so which is this distance, z in fact, plus the contribution of the compressive reinforcement, which is d minus d2. So it's d minus d2 times fs2. We can complete with the different variables of the value of the different values, and we have 1210 kilonewton meter. Now, just have a remark that the contribution, there is a small contribution of the compressive reinforcement. We will just now do the same calculations, but without compression reinforcement and see what the difference will be. So with this value, we see now that the tension force in the reinforcement is 2,562 kilonewton, compression force 431 kilonewton, and the force in the concrete is 2,134 kilonewton. The position of the neutral axis is 155 millimeter, and the stress in the tension reinforcement is 435, so this is yielding, and the stress in the compression reinforcement is 429, so this is smaller than 435, so this is fine, this is okay. Now we will have a look at the same calculation, but we will ignore the compression reinforcement. Why are we doing that? Well, we are in a simple bending situation and we want to use the concrete tables to get quicker the answer. So we'll do the same now, but with the compression reinforcement put into 0. So translation equilibrium gives us this simplified equation, and you have the direct solution of the value of x, which is now 186 millimeters. So you will see that the depth of the neutral axis increases because we left out force Fs2. It goes from 155 to 186. The rotation equilibrium is now also simplified, of course. This rotation equilibrium around tensile reinforcement. When we put in some numbers, we get 1173 kilonewton meter. Now you see that difference is 3%. When we take the compression reinforcement into account, we got 1,210. Without, it's 1,173. So it's only a difference of 3%. So we will now calculate the moment capacity in ULS persistence by using the concrete tables. So we know that the mechanical reinforcement ratio is defined by this. We put in the corresponding numbers, and we got that omega is 0.2814. We know directly from the concrete tables that we are in domain 2A. We have to make an interpolation of those two lines to find mu d, the reduced bending moment. We see also immediately that the steel in the tensile part is yielding, and that the filling coefficient and the delta G value is already known. And we see the concrete train and the train in the tension reinforcement. So we make the interpolation for the value of 0.2814 and the reduced bending moment must be 0.241. The definition of the reduced bending moment, from this we can calculate the design value of the moment capacity of the section. We fill in the different numbers and we got 1175 kilonewton meter. By doing by hand and not using the table, we found 1173. So you see, this is fine. So it's much easier to use the tables than to write every time the equation. Now we will calculate the moment capacity in the serviceability limit state characteristic. The compressive, the design value of the compressive strength of the concrete is 70 megapascal. B is 1 meter, D2 is 60, D1 was 64.5, the effective depth was 535.5, the cross-section of the tension reinforcement was 5,890, and from the compression reinforcement 1,005. So a capacity check in SLS, at that moment you have all those values. The K value is the effect of the permanent load divided by the effect of the total load, and this is 0.5 because the effect of the permanent load was equal to the effect of the mobile load. The elasticity of modulus of the concrete is then the mean value divided by 1 plus K phi, but phi in SLS characteristic, that is 0 because it's only with long-term loads that phi is different from 0. So it gives you a modulus of elasticity of 32,837. Okay, this is how we calculated the mean value of the elasticity modulus of elasticity of concrete. And alpha is then the ratio of the modulus of elasticity of steel divided by the modulus of elasticity of concrete, and it's 6.09. Okay, so this is fine. We know that in SLSK, the alpha is around 6. The position of the neutral axis in SLSK characteristic is equal to this formula. That's the depth of the neutral axis of the. It's in fact simple. You can take the cross section what we have and we make it in a fictive cross section, which means that you have the concrete section B times AH, but the plus alpha times the cross section of the steel. And in this section, you can take the depth of the neutral axis and you have this equation. So B was 1000 millimeter, S was alpha was 6.09, and these are the other values. So we put in the numbers and we find that X is equal to 160 millimeters. We just make a quick check. It must be bigger, of course, than the concrete cover plus the stirrup plus the point of gravity of the compression reinforcement. Otherwise, the compression reinforcement is situated in a tension zone, which is not possible. So X is 160 millimeter. The surface moment of inertia of the fictive cross section is equal to this. The bending moment is, of course, of the bending moment divided by E over V is equal to the stress. And this formula is valid for the fictive cross section. So it's valid for a section B times H plus alpha times AS1 plus alpha times AS2. So this is then the surface moment of inertia. Then we have the different values of the parameters. We can substitute all those parameters and find the surface moment of inertia. The bending moment is then given by the steel stress, by the concrete stress sigma c multiplied by E over V. We have already calculated E. The V, of course, is equal to X because this is the position of the neutral axis. Times 1818 is the maximum allowable concrete stress in SLS characteristics is 0.6 times 30 because it's about a beam inside a building. So it's 18 megapascal. Sigma S1 is then equal to this equation. And when you put in the different numbers, we got 257 megapascal. It must be smaller than 400, so that's okay. And the stress in the compression reinforcement, again, we can calculate it easily with this formula, which is derived by equivalent triangles. And we obtain 69 megapascal. Now we will look at the moment capacity in SLS quasi-permanent. These are the different values of all the parameters. We again now look at the K factor. QP, the effect of the permanent load was equal to the effect of the mobile load, so the K factor is 0.5. The concrete modulus of elasticity, the mean value of it is 32,837. And for this, then the concrete modulus of the modulus of elasticity of the concrete is the mean modulus divided by 1 plus k phi. Phi is the creep factor, is 2, and k was 0.5. So the modulus of elasticity of the concrete is half of ECM, which is 16,418. Alpha is then equal to 12.18, and this is what we expect. We expect a value around 15 in SLSQ. The depth of the neutral axis of the fictive cross-section is then equal to this. We calculate with all those parameters that we've got. Then we calculate the depth of the neutral axis, and which is 208 millimeters. This must be bigger than, of course, the concrete cover plus the stirrup diameter and the point of gravity of the tension reinforcement or compression reinforcement, or then we see that this is okay. The surface moment of inertia of the fictive cross-section, we recalculated this time with alpha equals to the value that we had on the previous slide, alpha equals to 12.18. Substituting for all the variables gives us this value as surface moment of inertia. The bending moment is then equal to the maximum concrete stress multiplied by E over V. And the maximum concrete stress in SLSQ is, of course, 0.45 times the characteristic value and gives you 13.5. E over V, E we have calculated, and V is, of course, equal to X. So the bending moment in SLSQ is 712 kilonewton meter. We check the tension or the stress in the tension reinforcement. Gives you 259 megapascal. It's smaller than 400, so that's fine. The same, we calculate the stress in the compression reinforcement, and we have 177, which is fine. Now we will have a look at the shear force capacity of the section with only contribution of the reinforcement. So the shear force is the reinforcement for shear times the steel stress. So VRDS is equal to the shear force, reinforcement, and the yield stress of the shear reinforcement. But ASV is equal to the cross-section of the shear stress or shear reinforcement multiplied by Z cotangent theta, which is the width of the compression struts divided by the distance of the legs of the shear reinforcement. So when you combine those two, and we know that cotangent theta is 2, then you have the best condition. FYVD is then of course 435 megapascal, the yield strength of this shear reinforcement. The shear reinforcement is diameter 12 with 4 legs, so it's 452 square millimeter. Z, the lever arm, is equal by definition to 0.9 times D, which is 482 millimeter. And so VRDS is then ASW over S. S is the stirrup spacing. And we find 632 kilonewton as shear force capacity.